recap the previous lecture once, because it also like more than a week. So just recap it and then we will go ahead from there. So in the last class we were discussing about the different quantities of the response spectrum. Okay, so we have introduced 5 different terms. What are they? So we have primarily 3 response: acceleration, velocity, and displacement. So these are the 3 prime responses we know, but from there we saw that there are total 5 quantities are coming. There is 2 pseudo and others are the spectral. Okay, so we have, so which one is only one? Displacement is only one. There is no pseudo spectral or spectral. There is only spectral displacement, HD. Okay, and other two has like pseudo spectral velocity and spectral velocity and pseudo spectral acceleration and spectral acceleration. Okay, we have also discussed it, that how the things are actually happening. So it was like that, like you have a, let's say you have a building, base is moved by y double dot and your top is moving by x. So we can say that mx double dot will be the acceleration, and we can write it mx double dot plus cx dot plus kx, that is equal to 0. That's with the forces. Okay, so this, and then your base excitation is at bottom. So what happens, the base is actually shifted by some amount. So once the base is gets shifted by some amount, that means you are having here that is will be not this one, that will be c into x dot minus y dot plus k into x minus y, that will be equal to 0. Okay, so that is the basic equation of motion. Once the structure is subjected to a base excited ground motion, which having the acceleration of y double dot. Okay, so we can write this. Now if we are putting it in the relative coordinate, let's say z. So z is the relative coordinate, which is from the ground we are measuring. So z, we are assuming it x minus y. So in that case, if we are substituting it here, what can we say? We can say this plus cz dot plus kz should be equal to minus m y double dot. Makes sense? Minus or plus? Minus. Perfect. Yeah, it will be minus. That's it. Perfect. Okay, so we will have this. So now once we are solving this equation, so now if I just go one step ahead, we will get z double dot plus 2 xi omega z dot plus omega square z should be equal to minus y double dot. So this equation of the single degree damped single degree freedom system is dependent on what are the parameters? But on what are the parameters this response is dependent on? Okay, first thing, what are the known thing? What are unknown? Known thing is z is known or unknown? Z is unknown. So z dot is unknown, z double dot is also unknown. So these 3 are the unknowns. What are the known thing? Zeta. Yeah, so zeta, 2 xi. So xi is known parameter. So 2 xi, then two xi omega is also like a varying parameter, like, so this full thing, and y is y double dot is known parameter. Okay, so these are the unknowns. Y double dot is known. So this full thing for a particular y double dot, this full thing is dependent on the two parameters, xi and omega. What is xi? Xi is the ratio of the damping or the damping ratio, and omega is the natural frequency of the structure. Perfect. So we can say that Z is primarily is a function of xi and omega for a particular y double dot, because y double dot is a signal. It may be earthquake, it may be wind, whatever it could be, or maybe some machine is running, so that machine signal, whatever. So y double dot is that type of signal, and Z is the relative displacement of the structure from the base. Okay. So now if we are taking, so now suppose what happened, we have a ground motion, let's say this one. So that is my y double dot with time. So I applied that thing on a structure. So that structure has mass is 1, stiffness is omega square, and its damping is xi. That's the equation actually. So this represents this. So I am implementing this motion at the base, and at the top I am trying to calculating what is the value of Z. So I will get 3 responses. Okay. First is I will get Z variation with time. Then I will get Z dot with time. Then I will get Z double dot with time. Okay. Agreed, all of you? Any doubt? Anyone? I think this is pretty straightforward thing. We will put the signal here, and we will get at the top some signal for a particular value of time period t, or particular structure, or maybe you can say omega square, and a particular value of xi. Okay. So from here, what can we do? We can select the peak. So peak can be top, it can be bottom also. So it should be maximum of the absolute of Z. Maximum of absolute of Z. It can be negative value also, can be like suppose in top it is maybe coming point, let's say 2. 0.2 is coming at the top, and bottom it's coming minus 0.25. So you should consider 0.25. Okay. Okay. If it is coming 0.2, if it is coming minus 0.25, your max Z should be, max of absolute of Z should be 0.25. So that is maximum of absolute of Z we have to consider, and that is nothing but my SD. So SD is representing what in this equation? What is represented by SD? Means we are having these two equations, maybe equation number 1 and equation number 2. So what is represented by equation number 2 or equation number 1? Means maximum of Z. Or if you think it from the physical point of view, that is the maximum displacement of the story, or you can say that maximum displacement of that single degree freedom system with respect to the ground. So this is the maximum story drift in the building. If you see, once we are meeting the serviceability criteria, we have to meet that the maximum story drift should not be more than that, and that is the meaning of the SD. Got that point? If the SD value is become too high, that means what? Your structure will go and come like this way. Okay. So higher SD value shows you will have a higher roof displacement. Okay. So like you are sitting in the building, you will go and come. I am not telling how much force it is attracting. It is just a measure of how much maximum displacement will occur. Okay. So that is the SD value. Clear up to that? Okay, good. Now, second thing is what? Second thing is coming that SPV. SV, first SV. SV is max of Z dot. Max of mod of Z dot. Means always it should be mod because or absolute you can say, because it can be negative also. Negative positive is just the direction, but once you are considering any practical point of view, you have to design for both, because the direction can change, so you cannot really be on that. So SV is this maximum of Z dot, and SA is max of Z double dot. So SA basically tells how much acceleration can be seen by the structure, or what is the maximum inertial force coming on the structure. That we can able to see by Z double dot, max of Z double dot. Okay. Now the question comes, what are the pseudo? So we have seen that SD has no pseudo. SD is SD only. So pseudo business is coming in the SV and SA. So SPV, that is a pseudo spectral, that is omega into SD, and SPA equal to omega square into SD. So please pay a little bit attention on that, this equation. Maybe I'm just writing it again. Z double dot plus 2 xi omega into Z dot plus omega square into Z, that is equal to minus Y double dot. So now if you see that we are dealing with the maximum values, so once the Z is maximum here, so this point is like omega square of SD, because Z is maximum, so omega square of maximum of Z, that is also the maximum of this particular term. Agreed, all of you? And this term signifies what? If I try to see what is this term, this is inertia force, because this is basically means although you can say it acceleration also, but if you think that the mass is 1, and if you think it that way, then you can say this is the inertia force. Then second term is, so this is my inertia. Second term is damping. Third term is restoring force or elastic force, and Y double dot is, that is Y double dot, that is the ground motion. So you can see that the restoring force, the maximum restoring force, is actually this much, SPA, omega square into SD. And that is the term what we are looking for any structural design. Because once we are doing a structural design, what we are looking for? What is the seismic demand? We have two things. One is capacity and another is the demand. So how much is coming here? So how much force the structure will be undergone, that will be the seismic demand. So that seismic demand will coming from SPA, and therefore code is giving that SPA value, because you have to ultimately design the structure. Why will you use the code? To design a structure. So you need to know how much force is coming to the structure, or for what force you have to design your member. There is also another way we can also able to think it. If I see from, means that explanation is coming from equation number 2, because that is equation number 2. But now if you see from equation number 1, which is really the term of the restoring force, that is mz double dot plus cz dot plus kz equal to minus my double dot. So there also, if you see that k into z is your restoring force. Okay, so restoring force is k into z. So when it can be maximum? So you can say that it will be maximum in k into max of z. So I should say k into sd should be the force. Then why there is a controversy? Which one is the force? K into sd or SPA? Now here there is a very critical point. Measuring the stiffness of a structure is very complicated. Comparatively, measuring the mass of a structure is comparatively much easier, because you know, like for example, if I just think like a building basically made of 3 components, just I'm very simplifiedly I'm thinking, like you have a slab, columns and foundation. I'm not going into beam and all other things, because now if you think the lateral stiffness contribution, so suppose come for the mass first. So mass is mostly come from the slabs. Okay, columns maybe some, it's also weight is much lesser compared to the slab, so maybe some percentage it is contributing. Okay, foundation is not contributing the mass for the floors. Okay, now if we are thinking the stiffness point of view, now the first and foremost question will come, what type of rigidity you have in the junction, and that becomes very subjective. You cannot directly able to measure that how much is the rigidity and all other things. So estimation of the stiffness itself is a big problem. Okay, so how we can able to bypass that point? We can just say that this is m into omega square into sd. So k can be written as mass into frequency square. Again, maybe you will feel, come on, if you cannot able to measure the stiffness, you may be able to measure the mass. Agreed? But you was told that you cannot able to measure the stiffness. So in reality, how can you able to measure the frequency? There are also some technique like the ambient vibration and all other things. So there we can able to measure the frequencies. Like if we place the accelerometer on the buildings, and if we just take the readings, we can able to see, due to the ambient vibration, some points we can able to see the peaks, and they are primarily the natural frequencies of the building. Okay, like for example, some vehicle is moving and all other things are happening, so due to some transient vibrations, the building will get little bit of vibrations, and that can be measured in the accelerometer, and from that reading we can able to find it out where are the peaks. So that can be some sort of estimation of the frequencies, that okay, this is the frequency of the structure. Okay, so estimation of frequency is relatively easier compared to the estimation of the stiffness, because suppose if you need to estimate a stiffness, you have to literally push the building, then only you can able to estimate it, and that is not possible. Like pushing a building, come on, that's not possible thing. So therefore people do not go in that way, and rather they follow this m omega square sd. So now m into SPA gives you how much force is coming on the structure. Does that make sense? That why all the codal provisions, not only Indian code, all the codal provisions just give the SPA. They don't bother with other 4 parameters, because once like all the code has chosen a single parameter, that must be significant enough. Otherwise they cannot just randomly choose one particular parameter and just forget all other, because that is the need of choosing SPA. Okay, one very important disclaimer, that Indian code also choose SPA, but they wrote it SA. So don't get confused. That is not at all spectral acceleration. That is pseudo spectral acceleration. Okay, that terminology is different, but they have written it clearly, that is pseudospectral acceleration, but they use the term SA. But in the structural dynamics context, we use this term as SPA. Okay, so don't get confused with that. That is also pseudospectral acceleration, and all the codes ASC, ACI, I don't think ACI has that, ASC, Euro, all those codes has the same SPA concept. They all are giving the SPA, no other values. Okay, good. So now, okay, so what are the utility of the other things? Like why the other things are or where it could be used? So now if you see, so we have already seen that SD gives us drift or maximum story displacement or maximum roof displacement, drift or max roof displacement. But unit need to be properly checked. That is the very important point. Means you should not get messed up with the unit. Okay. So maximum roof displacement or drift we can get from SD. SPA is the most important term that gives the estimation of the forces, how much is coming on that. So that is gives the elastic force on the member. I think all of you understood. Any question also, please feel free. Okay. Now if you see SA, what is SA doing? SPA we understood, what SA is doing. SA is actually telling how much acceleration is coming on the structure. Like if some of you are going to design some very specific lab, you maybe need to encounter with the SA. Like for example, there is a lab which has some type of radar, and you need that radar should not vibrate at all. These are sometimes important for some application of ISRO, some application of defense also, maybe sometimes these are very much required. For other purposes, these are generally not required. So, or maybe very sensitive equipments are there. So those things you do not allow any sort of accelerations in that equipment. So those things should be preserved in such a form that your acceleration of that particular flow due to any type of excitation should be within that limit. So these are some of the cases where these things is required. But in those type of specific applications, that could create a lot of problem. And also in the defense cases as well, like maybe they will miss some flight or something. So that is also very much important. But in normal day-to-day applications, not that much required. Okay. So these are, so this is the thing. Then, now what is the SV and SPV? So we understood the three terms, SD, SPA, SA. Now other two terms, SV and SPV. So SV is the spectral velocity, that is to estimate the total damping force. So spectral velocity helps to estimate the total damping force. So you see here, that is also C into Z dot. So once you are taking the maximum value of that, so C into max of Z dot. So that will be your maximum damping force. How much can be taken? So that is coming from SV. Okay. So what is SPV? What is pseudospectral disturbance? That is something not that intuitive. That is actually the maximum strain energy of the system. Maximum strain energy. Okay. So what is the maximum strain energy? That is Emax. That will be half of K into Z max square. Okay. Now if we put half of k is m omega square into z max square. So you will have half of m into omega into z max whole square. That will be half of m into spv square. So that is the measure of the strain energy. So for that thing you need SPV. But these parameters are very rarely used. Like, okay, you are measuring the strain energy, and means in the real life designing problem, not at all. Maybe some specific problem this could be used. Some of the cases again from the defense application, like for example, you are trying to make some shelter where there could be some sort of blast load or something. So that actually dissipates some of the energy. So they actually have to calculate that how much cycles or how much energy cycle it can able to take. So in those cases, these are required. But these parameters are not for day-to-day building calculations, not at all. Okay, so let's try to do one case and try to see that how we can able to get all those responses. Okay, so I am not doing it from time history. Let's first consider the Indian Caudal Spectrum, SPA. Okay, Indian Caudal Spectrum is given. So just start from there. Then maybe we will try to do one case where we will have that particular signal and we will do that. So Indian code, if I just think, that is written SA by G, but for our case just consider it SPA by G, otherwise we will get confused. So SPA by G, okay, so that is starting from, what is the value here? So this is time period. So what is the value here? Yes, anybody? 1, exactly. Can it start from any other value except 1? Why? Exactly, it's a rigid body motion and it's defined like that way. I explained in the last class also, like if you are putting the accelerometer on the ground, or maybe you just take a concrete cube, put it on the ground and put the accelerometer on top of it. So what will you going to measure? You will just measure the ground vibration, nothing else. No amplification, no de-amplification, nothing. Dynamic amplification factor will be just 1 at that particular point. So this is a rigid body. So therefore it will be exactly 1. It will always start from 1. And that point is known as two name. It has two names. PGA, that is good. And another name? ZPA. Yeah. So one is the PGA, peak ground acceleration, and another is the ZPA, zero period acceleration. Okay. Good. Then it goes like this. So what is that time period here? 0.1 second. Industry guys will just remember it all the time they are doing that. Then it will go. Okay. Here there is a 3 different cases given for the 3 different types of soil, and then it will go down and it go up to what point? 6. Think this value is, so let's say just this is rock. So for rock this value is how much? 0.4. And this goes up to, that is not given in the IS code. So that goes up to 4 seconds. After that, this graph is not given in IS code. That is maybe in ACI or some other, AC or Eurocode, that portion is given. Okay. So now, if you see, the first portion equation is 1 plus 15t, I think. And this value is going up to 2.5. So they are very standard thing, means everybody should more or less remember that. At least for the rock, it is very simple thing. Other case, yeah, means if you just ask me that, okay, for soil what is, I may be not able to say, but at least one case we should all try to remember. That is not that difficult as well. So that will coming like if you see SPA by G, that will be equal to this. So that is like T is less than 0.1 and is 0 greater than T is less than this. So suppose if you substitute T equal to 0.1, how much will you get? 1 plus 1.5 into 0.1. Sorry, that is 15T, not 1.5, 15T. That will be 1 plus 1.5, that is 2.5. You see, that is 2.5. Then you have a constant, that is 2.5. That is 0.1 less than T less than 4. Okay? 0.4, 0.4, yes, right. And then what should be the equation? Again, very simple. If you forget it, just assume how I remember. Assume this is 1 by C by T. Okay, now calculate what is the value of C. How you can calculate the value of C? That will be 0.4 should be less than T, should be less than some value. In Indian code, it is just only written more than 0.4. So if you just substitute 0.4, you should get 2.5. So 2.5 equal to C divided by 0.4. So what should be the value of C? 1. So that is 1 by T. And now if it is changed, like I think one case that is 0.6 or 0.66 maybe. So if it is 0.66, then you can put it 0.66 here. So 2.5 into 0.66, so that should be the graph of the equation of the graph. Very simple. Okay, so like this way the equation will come. Simple, not a big deal. And these portions are actually like parallel, like this way, going like that. Okay. So here this goes up to actually 4 seconds. So what, and importantly, the other part will be with 1 by T square or something like that. Okay. So now if I try it, so this is my SPA. So SPA is what? SPA equal to omega square times SD. Okay. So and then SPV will be equal to omega times SD and all other things actually. So if first thing is the target of to calculate, or so if I just write SPV, that will be nothing but, so I just do it, SD will be equal to SPA divided by omega square. So that will be omega into SPA divided by omega square. That will be 1 by omega into SPA. That will be T by 2 pi into SPA. Can I say that? That SPV equal to T by 2 pi into SPA. And SD will be equal to T square by 4 pi square into SPA. Okay? Makes sense? This value is nothing but 1 by omega square means T square by 4 pi square. Okay? We'll get that. So now start converting. Okay, now here, very important point. This is SPA by G. And if I just say that the zero period acceleration of that location, so let's say I just tell that ZPA or PGA value of that location is something like, let's say 0.3 G. That means what? That is something like 0.3 into 10 meter per second square. Just assume G equal to 10 meter per second square. Okay. Otherwise, you need to put 9.81, all those things. Just put assume 10. So that will become 3 meter per second square. So that 3 meter per second square is what? Please, ground acceleration. So that means now your SPA. So now you just plot SPA curve, not SPA by G or something. Now if you just plot SPA curve, you will start from what point? 3, exactly. And your unit will be meter per second square. Agreed, all of you? So it will be basically starting from 3, then it will be go for 3 into 2.5, whatever it is, and it will go, again it will go like that. So just basically you have to multiply this full set with 3 and your unit will become meter per second square. Any doubt? Any doubt? This is just you are scaling up, nothing else. Agreed, all of you? Perfect. So if you agreed, now let's move to the next point, that SPA we got. Now once we got SPA, so how to calculate the, so now your SPA will become 1 plus 15t into 3, then it will become 2.5 into 3, that will be 3 by t. Okay, these are the 3 values. So what will be my SPV? My SPV will be 1 plus 15t into 3 into t by 2 pi. That full thing will be multiplied by t by 2 pi. How much is the 3 into 2 pi? That is 7.5, na? 7.5 into t this, and that is 3 into very important point. Please try to note. You see, SPV value become constant. So this one is the range 0 less than t less than 0.1. This is the range 0.1 less than t less than 0.4, and this is the length 0.4 less than t less than 4. Now you see your SPV is constant in that region. You have seen that SPA was constant here, SPA constant, and here you see SPV become constant, and after that you can see that your SD will get constant. Okay, so first if I try to plot that, how it should look like, please tell. First portion, how it should look like. So first it will start from what point? If I put t equal to 0, it will be 3. Come on, it will be 0. Full thing is multiplying by t, and if you put t equal to 0, it will be 0. Simple. So it will not start from 3. It will be starting from 0. Make sense? So very important point. Acceleration has some value, but this velocity does not have any value at 0. That will be 0 straight. Okay. Now, so it will be the curve. What type of curve you are expecting? Parabola. Exactly. It will be a parabola going up or going down. It cannot go down, obviously, so it will be up only. Next thing is how it should be. T is increasing, so it will go up. Then what will happen? Constant. New type of response spectrum. By the way, have you seen that SPV spectrum? हाँ, आप लोग देखे होंगे, मैं मना नहीं कर रहा हूँ. But others, have you ever seen the SPV spectrum? Okay. By the way, where did you use that SPV spectrum? I have not used. Okay, so there you have seen that. Yeah, exactly. There you have seen that. Okay, perfect. Yeah, otherwise it's very uncommon to see SPV spectrum because SPV spectrum is the least used thing. You have seen that is only required for energy calculation. Otherwise, it is not at all required. So why people will be going to use that? And all the time designers complain that they did not get time, so they don't have a choice to use SPV spectrum and all those things. Yes, so now the next one, maybe the most important one, SD also. One of the most important. How it should be. So you already have SPV. So now you can just do it like this way. SD will be equal to 1 plus 15t into 3 into t square by 4 pi square. So at 0, what will be the value? 0. So this will be also starting from 0. Now you can also see 7.5 into t square by 4 pi square. Yeah. So you see the first portion will be much more stiffer, that increase. Then again it will be a parabola. Then you will have a straight graph, and then next phase you will have a straight line here. So which is more than 4 seconds. That is beyond the 4 seconds. But that graph equation is given in AC. In IS code, that graph equation is not there. So it is pretty difficult to actually do that also. So you will have this type of thing. So we can see that in case of the response spectrum, like the normal one, that is SPA, if we see, we are first having a increased acceleration, then acceleration get constant, then you will have a velocity control range where the velocity is constant, then you will have a displacement, constant displacement range, which will come beyond the 4. And in all the cases, like suppose once we are trying to designing a structure, we try to avoid the structure from 0.1 to 0.4 range, because it will attract more earthquake force. Makes sense? So we generally say that, okay, for case of the tall building, the effect of earthquake is less, because in case of the tall buildings, if I just think about our thumb rule that 1 story equal to 0.1 second, like a very gross thumb rule. So then this point is coming from 0.1 to 0.4. So that means 2 story to 4 to 5 story buildings are very much susceptible to earthquake, and it is attracting more forces because this is in the region of highest value of SPA. Agreed? That is not wrong. That is correct point actually. But so we also mentioning from that aspect that, okay, tall buildings, like let's say a building having a 60-storied height, 60-storied building. So from the thumb rule, its time period should be more than, I mean, it will become 5 to 6 seconds. Okay, generally that formula gives the higher side of the time period, so it will be generally lesser. So I can say that 5 to 6 seconds will be the time period. So 5 to 6 seconds time period means it is having very less amount of SPA. No doubt, because SPA will be very less in that region. So it is not attracting that much of earthquake force. So what's the problem? Why people are not doing all the buildings, tall buildings? So that's much better. So where the problem will come? Exactly, the displacement. You see, HD value is, they become so high. Means maybe you are sitting at the top, your building does not feeling that much of forces, your columns are not feeling that much forces, but you are like in the merry-go-round, going like this, swinging. So that will create a problem. For example, if you, so that problem, if you see in case of the wind turbine tower also, that at the top there is a very heavy mass also. So what happened, like once the earthquake or something happened, it will not attract that much force, but top is going to displace like this one, and that creates some definitely big challenges, because there are some machineries and they are undergo to this type of vibrations. So that's the problem. I hope now you get an idea where we are actually, like, suppose if you want to put some portion, like you want to control the force, you are actually creating hamper in the displacement or some other places. In this portion, you see that deviation is very high, that is with the 15 times variation, means the weightage is 15 times. Like suppose instead of 0.1, if you just put 0.09, that variation in the time period is nothing, that is like maybe although that is not small, that is also 10% variation, but yeah, your SA will reduce it to my SPA will be reduced in a significant extent. So therefore, what recently Codal provision means 1893 part 1, they suggested that forget that part, that is straight. We have to just take that straight value 2.5, simple. We have no other concession on that. So until and unless they are giving that code, so let's just discuss one or two very quick point on the very basic philosophy of earthquake resistant design. Although that is not the completely part of this course, just like for the basic understanding. So one thing we have seen that using the structural dynamics concept, we try to calculate how much forces are coming on the structure. And there is another thing is that we also estimate the capacity of the structure. So from there, we try to balance it. And that is known as the capacity based, that is known as the, like you have to plot the capacity spectrum and the demand spectrum. So once it is cutting at that particular point, you basically should design it. Okay, and also another important aspects we try to follow once we are doing the earthquake resistant design, that is we try to go for seismic fuses. So like let's say you have a chain, like a long chain, we all have seen, like maybe some rings are connected and making a long chain. So now if you are pulling that chain, when you can say that chain is going to break? Any of the member is going to getting breaked, you can say that will be lead to the full failure. So is it like any of the member or all of the member? Any, exactly, it is any of that, exactly. So in case of earthquake resistant design, we try to do what? We try to make that all the rings, and so to ensure that you should ensure that your load on the chain should be carried by all the member of the chains. Okay, and so each member of the chain should be more stronger compared to that forces coming. Okay, so that is like a very fundamental way of designing. And here that each member of the chain, you can think the different failure mechanism. Like for example, your structure may fail in shear, your structure may fail in compression, maybe some sort of buckling, global failure, local failure, plastic hinge formation, all those things you can able to consider like a club. And each are like each member means like each chains. Okay, member of the chains. So so once you are, so your each failure mode should be capable of taking more loads comparatively to the its failure point, so that your structure can able to reach the designed force. Okay, so that is like a normal philosophy of any design. But in case of seismic design, we try to do one step ahead. What we do now, once we check that, okay, like let's say there is a 7 members in that chain. So we say that okay, all the 7 members should have minimum that much of strength, that we ensure. Okay, now what do we do? Then we want that structure should be failed in this particular mode. Like let's say you told that the structure is going to fail, I mean you want the structure should fail in like a ductile failure. So maybe you are thinking that it should be failed in bending. So if you think that it should be failed in bending, what will you do? How will you ensure that point? You will make other failure mode more stronger compared to that bending failure mode. It does not mean you will make the bending failure mode weaker. Your bending failure mode should be as strong as that, but that is the weakest. But that is also has more strength comparatively whatever is required. It should be more than the required one. But that is the weakest among all. So once the failure will happen, you are ensuring that failure will occur there. So that is the philosophy actually adopted for designing the earth-resistant structures. Now if you try to see that how we can able to write a code and try to find a response spectrum for a particular excitation, so you can see that this is typically a code you can think. So first you have to, so this is the clear all, close all, these are the very standard. Then this is something maybe quite new, that is XLS read. So this actually reads some Excel file. You have to basically put the Excel file in the same directory, or you can also use some other way also, like you may give the path and so that you can read it at any particular point. So that, and then the seat number. So from there it will read that full data whatever you have given. So you can put here several data also. So accordingly you can able to plot the different types of thing. Then you can get like a T. So T is for the first row, then acceleration is the second row, then we are doing the absolute acceleration. So like this way we are going ahead with that. Then we are implementing the numeric beta method. You can see that's a numeric beta scheme we are implementing. Then we are defining some of the matrices so that we can able to run it, store the values and all those. Then we are going for the iteration for the response vector generation. So we started with Ti less than equal to 4.5. So we are not going after 4.5. You can change that value and you can run it as per your own. Then W equal to, so that is like a omega. So we have just calculated all those things here. Then we are running the for loop so that we can able to get the values as well, then acceleration, displacement, and now you can see that we are storing that J actually denotes at what time we are. So that is actually running the loop basically. So we are storing that SA value, SV value, SD value, SPV value, SPA value. So that are getting stored. So you can see that SA is just storing the maximum acceleration, SV maximum velocity, SD maximum displacement. We just stored that. SPV is nothing but SD into omega is, so that way we are calculating the whole thing. So this is coming here, and then we can able to plot like time versus SPA. So time versus SPA I have plotted and we got that. Then you can also plot the other values as well. So maybe if I just do like this way, figure 1 is this. Okay, so like let's see, we will have like 5 plots. So fifth one was SA, this one was SPA. Now this fourth one is SV, I think. This one is, so 1 and 5 has a big similarity. So both of them are the acceleration plot. 1 and 5 both are acceleration plots. So you can see that this is typically going up then go down and go down. Similar to the Caudal plot also. Obviously, as I told that you will not see the Caudal plot here directly, because Caudal plot is the average of several earthquake responses. You will not get from a single earthquake exactly the Caudal plot. That is not possible. You have to run it for like maybe 200, 300 or maybe some 1000 plots. If you run, maybe you will converge to there. Okay, so that is for the acceleration case, we can see. Then next case, so this is the velocity plot, so two velocities. So you see that jump is getting literally reduced, and still you will for the higher range, which is like a less value, but displacement case you see it is going up, and that the very similar thing you can also able to see from the Caudal case as well. It is going up, so and then go right. And also to see here, and obviously, as again I am mentioning that you will not get exactly plot from a particular earthquake. You have to do it for thousands earthquake. If you run, now you will able to see that profile is some sort of like a response spectrum. From one, not possible, because here actually if you see, particular earthquake may have some predominant frequencies, so it will excite that structure in that particular frequency, so you will get a charge at particular point, but that is maybe not for the other, so that will get diminished for the other point. So that actually happens, and you can also change the damping so that you will get the different type of damping curves as well. So like this way we can able to do that. Okay, so with this maybe we are closing today's session. Thank you very much to all of you.